Today's computers are getting smaller and faster day by day because electronic components are getting smaller and smaller. But this process is about to meet its physical limit with computer parts such as transistors approaching the size of an atom. However, to overcome this limit and drive computers to more progress, the usage of quantum mechanics must be implemented in computer hardware. In a nutshell, quantum mechanics investigates the physical universe at its most fundamental level. Particles behave differently at this level than they would in the classical universe, taking on several states simultaneously and interacting with particles that are extremely far away. But before diving deeper into the subject, some historical context would be welcome. Richard Feynman ignited the flame of quantum computing. He raised the following challenge in 1981 at MIT. Classical computers cannot effectively simulate the development of quantum systems. Thus, he put up a fundamental design for a quantum computer that could do the simulations. With this, he demonstrated how conventional computers may be exponentially outpaced. But it took more than 10 years for the Shor algorithm, a unique program, to be developed and revolutionize the way people think about quantum computing. The technique, created by Peter Shor in 1994, enables quantum computers to factorize huge numbers effectively and exponentially more quickly than the best classical approach on conventional machines would. But we will talk more about Shor a bit later. A quantum database search technique was created in 1996 by Love Grover and offered a quadratic speedup for a number of issues. Any issue that required a random or brute force search could now be resolved 4 times more quickly. Grover's algorithm and other pioneering quantum algorithms were successfully solved in 1998 using a functional 2-qubit quantum computer. More and more applications were created as the race for a new era of computing power started. Since then, several tech giants such as NASA and Google started investing massively in quantum computing research. However, the race reached a new level in 2017 after IBM unveiled the very first commercially viable quantum computer. So, now that we have a brief introduction to the field's background, let's dive and see what actually is quantum computing. So, as a quick reminder, normal computers represent data as bits, which either take the value of 1 or 0. The quantum analog of bits, named qubits for quantum bits, can also be set to one of those two values. However, in the quantum world, the qubit doesn't have to be one of those values and can be in any proportions of both states at once. This is called superposition. So we can view a qubit as a superposition of probability of it being 1 or 0. But as soon as we measure a qubit's value, it has to decide whether it is 0 or 1 and collapses into one of those two states. Superposition is the property that makes qubits so useful. For example, if we take a 4 bits combination, it represents 16 possible values in total. However, when it comes to qubits, all 16 combinations are possible at once, since it could be any of them. Another important quantum property is entanglement. It is an extremely strong correlation that exists between quantum particles. So strong, in fact, that two or more quantum particles can be linked in perfect unison, even if separated by great distances. When one of these qubits is manipulated, the manipulation happens instantly to its entangled twin as well. We can also add that just like operations are performed by logic gates in regular computers, they are performed by a quantum gate which changes the state the qubits are in. For example, let's take a 2-qubit state of 0, 0 and process it through a quantum gate. We then have the resulting superposition of a 1/2 probability of being 0, 1 and a 1/2 probability of being 1, 0. Now let's see it from a more mathematical perspective. So a qubit with two states is typically presented using the ket notation, with the number 0 or 1 being the qubit state. Then the superposition has the form alpha times ket of 0 plus beta times ket of 1, where alpha and beta are complex numbers satisfying the absolute value of alpha squared plus the absolute value of beta squared equals to 1. This kind of looks like probabilities, doesn't it? So alpha and beta are the amplitudes or the probability of the state being either 1 or 0. Let's take the 6-qubit quantum computation. Since a classical computer can only be in one basic state at once, computing this would require thousands of steps, since each branch would need to be calculated separately. In contrast, the algorithm only needs 4 steps on a quantum computer, since it can calculate an entire level of the tree at each phase. So, quantum computation is exponentially quicker. However, this represents a huge problem for modern cryptography and security, since crypto systems could be cracked way easier because of its ease to factor big numbers. And a good example of this is Shor's algorithm. So in 1994, Peter Shor developed his algorithm allowing quantum computers to efficiently factorize large integers exponentially quicker than the best classical algorithm on traditional machines. The latter takes millions of years to factor 300-digit numbers. Theoretically, the Shor algorithm is capable of breaking many of the crypto systems used today. So, to factor a large number n into two primes, Shor's algorithm changes the problem of finding the factors of a given number to finding the period of a function. Here are the algorithm's steps. So the first step consists of picking a number a that is inferior than n at random, and to make sure that it's not a factor of big N. The second step is finding R, which is the order of A mod N. The third step is checking that R is even and that A to the R over 2 plus 1 isn't congruent to 0 mod N. The fourth step, which is the last one, consists in putting P, the GCD of A to the power R over 2 minus 1 and N, and Q, the GCD of A to the power R over 2 plus 1 and N. And here you have two prime factors of big N. But the most difficult step here is the second one. It is a discrete logarithm problem, which, as you may know, gets harder if n gets larger. However, the order is a global property of this quantum superposition. We then apply what's known as the quantum Fourier transform to the superposition. This method uses quantum physics to amplify the basic states associated with the correct order so the incorrect answer's amplitudes are suppressed. We then finally obtain R. But how can quantum computers benefit to quantum cryptography? So quantum cryptography uses photons as qubits. Each photon carries an electromagnetic field with a specific direction, known as its polarization. The two states used to define qubits are horizontal and rectilinear polarization, both represented by 0 and 1. The polarization of photons can be influenced by the vertical or horizontal polarization filters that influence the output according to their match with the polarization of the photon in question. This is kind of the equivalent of a quantum gate in the case of photons. So, to have a better idea of it, for example, if a horizontally polarized photon is passed through a straight polarization filter, its state changes to the opposite. But if it is passed through an horizontal polarization filter, it keeps the same state. This phenomenon is what the BB84 key distribution algorithm, developed in 1984, is based on. In this one, Alice chooses a random set of bits that she will encode into photons polarized in a particular randomly chosen base. These are sent by public channel to Bob, who chooses random bases on his side and decodes the photons thanks to them. If Bob used the same base as Alice, he gets the same result. Otherwise, he gets a random result. On the same public channel, Alice reveals a subset of bits and the polarization chosen for these photons. If Bob used a different base, he ignores the result because it is random. But if he uses the same base, he should get the same answer. However, if he uses the right base but gets a wrong result, then his suspicions are aroused. Indeed, this system allows to detect if an attacker tries to crack the code. If the attacker tries to find the key by using polarization filters, then he would alter the message. However, there is still a chance that the attacker will hit the right combination, but the more photons there are, the more complicated it is, making it statistically almost impossible to find. The BB84 algorithm is then resistant to man-in-the-middle attacks, assuming that the attacker only has one chance to try his polarization filters. In this way, quantum cryptography and quantum computing are advances that would revolutionize our world, but for now they are mostly theoretical. Despite this advance represents major stakes. My discussion question would then be the following. How could databases and other systems requiring security using traditional cryptography adapt and survive the emergence of quantum cryptography? Feel free to answer your question using all your creativity and logical thinking. Thank you for watching.